Hello there. In this lesson, we're going to learn a little bit more about the mole and how it's related to a number of other measurements in chemistry. Measurements like volume of a gas, number of particles, mass, and a few others that you're already familiar with but didn't know were connected to the mole. So if you recall, the mole is an equivalent quantity of particles that is equal to the number of particles that you'll have for any of those masses off of the periodic table measured in grams. So for hydrogen, the mass off the periodic table is 1 gram, and that is 1 mole. That's one equivalent quantity of hydrogen atoms. And Avogadro's number is the quantity of atoms that is. And then it also works for molecules. So it works for any type of particle, whether it's an atom or a molecule or other type of compound like ionic compounds, which we'll get to later. So all you do for larger compounds is just add up the molar masses of the elements in the compound, 2 hydrogens and 1 oxygen. You end up with 18, and that's the mass of 1 mole of water molecules, and that'd be the same number of water molecules in a mole. So let's try using Avogadro's number with our factor label method. Here it asks how many molecules are in this many moles of carbon dioxide. So we'll write down what we're looking for here, molecules, and we have 0.25 moles of CO2. Now it doesn't matter what the substance is, there's the same number of molecules in a mole. So it's always going to be 6.02 times 10 to the 23rd molecules in 1 mole. There is no short form for molecules that I know of. Some students have shortened it to cules sometimes. It's up to you what you want to do, but I'll try to write it all out whenever I'm doing it here. Okay, so 0.25 times 6.02 times 10 to the 23rd is 1.5 times 10 to the 23 molecules of CO2. Great. And we can work backwards as well. How many moles? So moles equals 7.44 times 10 to the 24th molecules of CO2. And if we want to go from molecules to moles, we're going to need Avogadro's number again, just in the reverse. We're going to be dividing instead of multiplying, because there's that many molecules in every mole of CO2 in this case. So 7.44 times 10 to the 24th divided by 6.02 times 10 to the 23rd. And I get 12.3. 12.3 moles. Great. How many molecules are in 625 grams of CO2? Ooh, so now we're combining the Avogadro's number along with the molar mass that we worked on in the last lesson. So we're looking for molecules again, only instead of moles, we have this mass, 625 grams. So we're going to have to convert into moles first, and we know there's 44 grams for every mole of CO2. If you don't believe me, you can look up those masses on your periodic table. And once you have moles, see the grams cancel out here. Once you have moles, then we can use our Avogadro's number. So it's 6.02 times 10 to the 23 molecules for every 1 mole. And moles are gone here now. And so what do we got here? 625 divided by 44 times 6.02 times 10 to the 23 is 8.55 times 10 to the 24th. And that would be molecules of CO2. Great. So Avogadro, the scientist, did a lot of studies on gases, and that's why he eventually had Avogadro's number named after him, because a lot of those studies led to understanding of the quantity of particles in a mole. And so what he noticed, what most of his studies led to, was the fact that it didn't matter what the gas was. If you had the same number of particles, they would occupy the same space. And since we're talking about number of particles here with the mole, then 1 mole of any gas will occupy the same amount of space as long as the conditions are the same. Now you probably already know that if you have a balloon and you put it in the fridge or the freezer, it'll shrink, and if you put it somewhere warm, it's going to expand. But when the conditions are set, when they aren't changing, the volume of a set amount of gas will stay the same. And it doesn't matter what type of gas it is. So what he found was that under standard conditions, which are 101.3, which is like average atmospheric temperature, and 0 Celsius, any gas would occupy 22.4 liters. So if you had hydrogen gas and you had 1 mole of it under those conditions, that'd be 22.4 liters. If you have carbon dioxide gas under those exact same conditions, same exact space. It doesn't matter what the gas is. The size of the particles are so tiny compared to the spaces that the volume will be the same. So this only works at STP, and that stands for standard temperature and pressure. Now another standard that was also used is standard ambient temperature and pressure. Pretty much the same pressure, but the temperature is a little warmer, and so that means that the volume is a little bit greater. So at SATP, the volume is a little bit greater, the same amount of particles, 1 mole of any gas will occupy 24.8 liters rather than 22.4. So these are all per mole, per mole, per mole. There you go. So let's use that to figure out some volumes in moles. It says what is the volume? So volume equals 2.5 moles of CO2. Doesn't matter what the gas is. And we know it's 22.4 liters for every mole. And with our calculator, 2.5 times 22.4 is 56. 56 liters. Very nice. All right, then we can add our molar mass onto that as well. If we want to know the mass of carbon dioxide that occupies 15 liters at SATP, we can use the conversion for SATP, which is 24.8 liters in every mole of CO2. And then, since we're asked for a mass here, we're going to need the molar mass, which again for carbon dioxide is 44 grams per mole. All right, let's see how that comes out to. 15 divided by 24.8 times 44 equals 26.6. Rounded to 2 sig figs, 27 grams. All right. Okay, sometimes the word particle gets students a little mixed up, so I want to address that here. We've been using mostly molecules in our example here, like carbon dioxide, where a particle is a molecule of that substance. It's the smallest bit of that substance. So that works for all molecules, right? There's methane, there's water. It's very convenient to think of a particle of a substance when it's a molecule. So that's why we usually start off with those, because they're easy to imagine in your head. But if you got something like an ionic compound, it's not always easy to visualize what the particle is. And so sometimes the word formula unit is a little more descriptive and helpful, because what you're saying is if the formula for sodium chloride is NaCl, 1 unit of NaCl or 1 particle of NaCl is just whatever matches the formula. So just like CO2, it matches the structure for carbon dioxide as a molecule, you can take whatever the formula is for an ionic compound, and that'd be 1 particle of an ionic compound. So compounds like molecules or ionic compounds obviously have more than 1 element, and sometimes more than 1 of each type of element in their formula. And so if you want to find out how many atoms there are in a given quantity, you'll have to multiply by the number that's in the formula. So what does that look like? Well, questions like this: how many oxygen atoms are in 2 moles of carbon dioxide? So you know that carbon dioxide is CO2. That means for every one of these carbon dioxides, we're going to have 2 oxygens. So I'm looking for oxygen atoms, and I know I have 2 moles of carbon dioxide, and then I can use Avogadro's number to figure out how many molecules. So 6.02 times 10 to the 23rd molecules of CO2. And then the trick is to just look at the formula. You're going to get 2 oxygen atoms for every 1 CO2 molecule. And then you'll end up with your oxygen atoms, right? Molecules will cancel out, moles will cancel out, and you'll end up with what you looked for. So let's do this. 2 times 6.02 times 10 to the 23 times 2 equals, well, look at that. That's 2.4 times 10 to the 24th oxygen atoms. And the reverse also works. How many glucose molecules contain that many oxygen atoms? So glucose is C6H12O6. So every one of those glucose molecules is going to have 6 oxygens in it. So let's start with, we're looking for glucose molecules. And we started with 2.0 moles of oxygen atom. Should be O2, my bad. Let's get rid of that. Okay, so we can go from moles of oxygen to atoms of oxygen, right? So we know that there are 6.02 times 10 to the 23 atoms of oxygen in every mole of oxygen. And then once we have atoms of oxygen, we know there are 6 atoms of oxygen for every 1 molecule of glucose. And so you can see there, that's where I got the 6. And we see everything cancels out. Moles of oxygen, atoms of oxygen, atoms of oxygen. I'm left with molecules of glucose. That's what I was looking for. Great. So let's say 2 times 6.02 times 10 to the 23 divided by 6 equals. And I've got 2 times 10 to the 23 molecules of glucose. There you go. So finally, with all these conversions, it can be a little confusing at the start. To help you get used to it, sometimes the mole map is a graphical way for you to keep all these connections and all these conversions straight. So you can see that the mole can be converted to mass using the molar mass off of the periodic table, or you can convert the mole to a volume of a gas if it's at STP or SATP, because you know the molar volume, right? Or you can use Avogadro's number to get to particles if you have the number of moles. So all those connect to the mole in the center there. There's a few others that we can add on to this that you've already used in the past and that also will fit in here. So we can add density. If you know the mass of something, you can use the density of it in order to work out the volume. So if it was, say, a certain amount of water, you know, we have like 10 grams of water, and you know the density of the water is 1 gram per milliliter. That means you can convert into your milliliters, right? The other end here is what we've just been doing with atoms. And if you know the number of atoms per particle, you can convert into a certain number of atoms in the particles themselves. So there's a couple other connections you can add onto your map. And so whenever you are doing conversions, when you're learning especially, it can be nice to have a little graphical representation. So you can write this down on a piece of paper and follow it until you got good at your mole conversions. Alrighty, so here's a few we can try to use the mole map as a guide. So this one is asking what the volume of this number of molecules of CO2 is. So I have a bunch of molecules, so we'll start here. And we want to end up with volume at STP. We want to end up here. So we're going to have to do 2 steps from here and then here, right? So we'll write down volume of CO2 at STP. And we are given 8.4 times 10 to the 25 molecules of CO2. And we know that there is Avogadro's number, 0.2 times 10 to the 23 molecules per mole of CO2, right? So now we're at the mole here in the middle, and molecules cancel out. And we also know that at STP, there are 22.4 liters in every mole. So the moles will cancel out. And so with our calculator, we can work out, since we ended up with a volume here, it should mean we're done, and we've reached our destination here on the map. So 8.4 4 times 10 to the 25 divided by 6.02 times 10 to the 23 times 22.4 equals, wow, that's a lot of liters. So 3,000, how many sig figs I got? I only got 2. So 3,100 liters of CO2. There you go. That's a lot of CO2. All right, last one. How many hydrogen atoms are in 250 milliliters of liquid water? Ooh, so we're going from a volume over here. It's not a gas, and we don't have the conditions for it. So we're going to need the density to go to the mass, and then we're going to need the molar mass to get to the mole. Then we're going to need Avogadro's number to get to the molecules, and then we're going to need the number of atoms per particle to get to the atoms. So this is a long journey on the map. But we do it the same way. So hydrogen atoms equals 250 milliliters of water. And we know that the density of water is 1 gram for every 1 milliliter. So that gets us to grams of water. Ding, 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 we are at the mass. Next step, water is 18 grams per mole. You can check on your periodic table if you like. And that gets us to the mole. Next step, let's go to the molecules. We know that there's 6.02 times 10 to the 23 molecules in 1 mole of water or of anything. Great, we're at molecules of water. Now, how many hydrogen atoms are in a water molecule? Well, it's 2, it's H2O, so 2 hydrogen atoms for every 1 water molecule. And if we put that all into our calculator, all the units should cancel out. Milliliters, milliliters, grams, grams, moles, moles, molecules, molecules. We're left with atoms. Crowd goes wild. 250 divided by 18 times 6.02 times 10 to the 23rd times 2 equals 1.7 times 10 to the 25 hydrogen atoms. Okay, we'll talk to you soon.